What is a p sequence, and for what values of p does it converge, Johan?
For p sequence that is represented by 1 over I with the p, 1 over I p exponent.
Right.
And the local of that is I p is more than is greater than 0.
Got it. You did great. Just need to talk it out. Everything was perfect. All right. What about a p series? What is the p series? Lorenzo. Good. Right. Remember, so if p is 1, that's a harmonic series. If it's less than 1, it gets too big too fast, and it just goes up. But if p is greater than 1, then those denominators are small enough that that sum will level off and actually sum up to a finite value. Okay? Geometric sequence. What is a geometric sequence? Maya? R to the I. And when does that converge? Okay, and then the geometric, all right, so yeah, so R to the I. So we had our basic form of the geometric series is a little bit different. We include a coefficient A, and then we start at, yeah, so in the geometric series, we want that first exponent to be 0. In the geometric sequence, we could make it 0 if it was I minus 1, but we just talked about how the first in the sequence was just r to the 1. But in a geometric series, we want to include the possibility of just a, right? R to the 0, which is a times 1. And when does that converge? So we did this last time. When does the geometric series converge? Same, right? If the sequence converges, if the geometric sequence converges, then the series also will sum up to a finite value. Okay? How can you quickly conclude that a series diverges? This is what we talked about last time. Remember this? Justin?
Using the divergence theorem.
Okay.
If the sequence converges to a non-zero number or the sequence diverges.
Good. Right. So if the sequence converges to something other than 0 or the sequence diverges, we're done with this series, right? We're done with this series. It diverges. Okay? And then what is necessary for a series to converge? Here on the flip side. What must be true for a series to, yeah, Catherine? That's right. Sequence has to converge to 0. And does that guarantee that the series will converge? No. All right? It's just possible now. So it's necessary, but not sufficient. If the sequence converges to 0, that has to be true for the series to converge, but that's not enough, right? We have to make sure that now that there's the real question here, like, does that series converge to a finite value or not? All right, any questions? All right, so let's look at let's look at some more geometric series. We just kind of rushed that at the end. So remember we looked at this example. This was the turtle example, always walking half as far as the previous day. And just to get caught up here, we said that this is the same as 1/2 to the j. And to make it look like this form, a times r to the j minus 1, so this goes back to our understanding exponents, right? So I want that to look like something times r to the j minus 1. So how can I make those equal? So over here, so how many 1/2s do I really have multiplied together? J of them. So if I need to look like something times 1/2 to the j minus 1, what does that something have to be? So I still have j 1/2s multiplied together. I need one more 1/2, right? Because I just lost a 1/2. So I need one more multiplied on there. And now the reason I did this so it looks exactly like this, right? And then I can use, and this converges. Why? R is between -1 and 1. My R value is 1/2, so we know this is going to converge. And we derived the formula for the actual sum last time, which was A over 1 minus R. So when a geometric series converges, it converges to A over 1 minus R. And then we did the math. 1/2 over 1 minus 1/2. And that was 1. And that told us that if the turtle walks all infinitely many days, he does make it across the backyard. But as soon as he stops, then you've got a partial sum. Does that partial sum equal 1? No, it could be super close, right? Like so then the longer your partial sum is, the closer it'll be to this. That's a really key point, that partial sums are approximations of the sum. And the longer the partial sum, the better the approximation is. Super important point, right? Why? Because the sequence is going to 0, right? We keep adding a smaller and smaller and smaller number. That means what we've added up so far becomes a better and better approximation to the whole sum. All right, so partial sums are approximations of the series, and the longer the partial sum, the better the approximation. But if you kept walking an infinitely many number of days, then the turtle does make it across the yard. All right, new example for geometric series. So that's all review. Any questions? So this one. So this one's a little more involved here. But again, so first of all, we recognize that it's geometric because it's the i's are in the powers, right? So what do we have to do? If we want to figure out what this sum is, we know that's A over 1 minus R. We got to get it in the A times R to the J minus 1 form. So what is our R value, first of all? What is our R value looking at that? Do you see that it's -3/4? Because I got -3 to some power in the numerator and 4 to some power in the denominator. So what we want to transform this thing is to make it look like -3/4 to the J minus 1. Now the question is, how do I get it to be equal to this? So let's look at the numerator. So we have the 1/5. That's that 5 right there. Now, how many -3's do I have multiplied together? Oh, sorry, I should have put I, not J. So I minus 1. So how many -3's multiplied together? Dang, I keep putting die. It's J. All right, J. There we go. How many -3's multiplied together? What the heck? I had it right the second time?
Yeah.
It's my eyes. Those for a second there it looked like J's to me. Okay, it's supposed to be I or J? Okay. I think then I looked up there and saw J. Okay. All right, here we go. So I got I plus 2 -3's. And how many do I have here? -3 to the I minus 1. So how do I get, what am I going to need so that I have actually I plus 2 -3's now? How many more do I need? Not -3rd. I just need 3 more -3's, right? Aren't there 3 more -3's here than there are here? So then I need 3 more. So I'm going to do -3 to the 3rd. Or you could just write -27 if you want. Whatever that. Yeah. So now I have the same number of -3's. Okay, here I have how many 4's in the denominator? I minus 2. And how does that compare to 4 to the I minus 1? I have one more or one less now? This is one more. So I've got to kind of like get rid of one of these. How can I do that? Yeah, so in the denominator I could divide out a 4, or in the numerator multiply by a 4. So I'm going to do this. I'm going to do 1 down here in the denominator. I'm going to do 1/4. So I had I minus 1. When I divide by a 4, now I'll have I minus 2. That's what I need. So does it make sense what all these shenanigans, what I'm doing here?
Yeah.
Again, it goes back to just understanding exponents, right? Understanding what exponent means. I need to preserve I plus 2 negative 3s and I minus 2 4s, but I need to have negative 3/4 to the I minus 1 to make it be like a geometric series. So that's why I'm doing this. So therefore, now we can put together the A value. The A value is going to be, this is going to be 4 times negative 27 over 5. So I got 4 here, it comes up with the numerator, and then times negative 27 all over 5, and then negative 3/4 to the I minus 1. So here's my A, here's my R. Does this series converge? Right, because R is between negative 1 and 1. This is like a fractional amount of 1. And so it's going to converge to my A over 1 minus R. Four, negative 7, 5, all over, what is that, 1 plus 3/4, 7/4. Whatever that crazy number is. Anybody got it? So 16 times negative 27 over 35. Whatever that is. Negative 432?
Oh, negative 432
Over 435. So, what does this mean? It means that if you added up all infinitely many terms of this sequence, right? If you added up all infinitely many terms of this sequence, the sum would be negative 432 over 35. Any questions on that one? Are we good? Okay, so so you have a web work due tonight on kind of the basics of convergence of series. It's due at 5. And then the next web work will be on geometric series. And the next one will be like a double length one, which will just be analyzing all kinds of series. It'll be like a survey of all the series that we do, and that'll be like in a week or something. But with these web works, it's going to be more often than Wednesdays. So you just got to check Blackboard sometimes every class period or every other class period. So just keep checking Blackboard for when those web works are due, okay? All right, let's go on. So we already have kind of alluded to this one. So here's what we call comparison. If here's two series with all positive terms, and say we're analyzing this one. So we're given this series here. This is our given series. And the question is, does that series converge or not? And the idea is, here's another series that's similar that we know diverges. And then in the one that we're analyzing, every term of ours is greater than the terms of the one that we know. So the conclusion is that the one we're trying to analyze is divergent, or diverges, right? So that that should make sense in your head, right? So we're like, okay, what happened if we summed all these up? Oh, that's kind of similar to this one. And we know that if you sum all these up, this one diverges, and all of the terms in the one I'm working on, each term is greater than the terms in this one that I know diverges. So that will diverge then also, the one that I'm analyzing. So that, more than just memorizing, that should make sense. That idea should make sense. Doesn't it make sense? Okay, so I want you to given a series that you expect converges, how would you use comparison to prove it? Write out a statement similar to the one above, okay? So now you're working on one, you suspect that it converges. How could you use comparison to prove it or to justify that it does converge? So we want to write out something similar to this. That would be a way of using comparison to show that our series converges. Go, do it. I think you're getting it, but you're not saying it right. I think. Go ahead.
BI is less, and it converges, then AI.
Yeah, no, I think you got the idea, but you're not saying it right.
Just trying to negate the statement.
But here BI is less. This is saying BI is less.
Oh, okay. AI is less.
Right. Yes. I knew you had it. You just yeah.
Is it always convergent, or is it another might be?
No. If you know that BI converges and all your
Oh, converges.
Okay.
Oh, never mind.
So how would we write this out for a comparison test that shows that the series converges instead of diverges? Anyone want to? Yeah.
So if you have, like, if the series BI
Uh-huh.
is convergent,
Right.
and then AI is like less than or equal to BI,
Right.
then the series would be
Right. And this should be for all I. This shouldn't be n. This should be for all I. No, that's not your fault. That's my fault. Yeah. Yeah, right. So here it is. If your sum converges and all your terms are less than or equal to the terms of the sequence, then your sequence converges. All right, so let's practice that. So see if you can make some progress on these. So again, you're looking for patterns here to things that are similar that you know, and arguing by comparison that these either converge or diverge. So I'm going to finish attendance, and you can work on these. Go.
Do we have to do a comparison test? It's like an obvious one, like the first one, or is it like?
You have to use comparison for the first one. No, it's not obvious. It's obvious for the sequence.
Oh.
This is a series, though. We're adding them up. Yeah. So for a sequence, it's obvious, but for the series, you got to tell me why. Why do you think that converge?
This is 3 over R.
Here's a good justification. So this is an example of how you should justify this. I wrote converges since
Oh, yeah.
not since all my terms are greater than or equal to, less than or equal to, thank you. If you thought that was less than or equal to, all my terms are less than or equal to 1 over I cubed for all I, and that one converges as a P series with P greater than 1. So that's a good written explanation, right? So good mathematical justification. So keep going, go, keep going. Yeah.
Is I squared when that always converges to the first one? Like if you did for like the and summation of I squared converges to P greater than 1.
1 over I squared.
Yeah. Since that's P greater than 1, that should always converge to that.
And you're saying this is less than or equal to that?
Yeah.
That's okay. It just is a little more direct. Like you got to think more when you do that one. But this is just straightforward, right? Because you know I plus 1 is going to make I plus 2. It's going to make them all less. So it's okay. It's okay, but this is better.
Oh, that's actually so.
Okay, second one. Diverges or converges? Diverges or converges? Diverges because? All right, P is less than 1, but so what are you going to compare this to? You're going to compare this to what? These are all greater than or equal to what? If you're saying diverges, you're saying all those terms are greater than or equal to what sequence? 3 over radical I. 3 over I to the 1/2. And that series diverges or converges? That's P less than 1, right? So that diverges. And why are these all greater? Because you have a smaller denominator, right? You're subtracting in the denominator. That makes the denominator smaller and makes this fraction bigger than these. And when you sum up these, it diverges. So diverges. So what I said there verbally is what you would write out, okay? All right, how about this one? What do you think? Converges or diverges? So what you see here is that it's like 1 over, I stumped you there, I guess. It's like 1 over j times what? 5/2 to the, we could figure it out so that it's j minus 1. We might have some other constants in here, but those don't really matter. So I have 5/2 to the j minus 1 and 1 over j. What's that? 8, yes, thank you. Okay, good. This is 2 to the 3j. We'd have to make that 8 to the j first, so it's 5 over 8. Thank you. So, converge or not? Because? This would be a geometric series that converges, and then by multiplying it by 1 over j, our terms are 1 over 2, 1 over 3, 1 over 4, 1/5, 1/6, 1/7. What does that do to these terms? Make them bigger or smaller than this? Smaller, right? So this is our geometric series converges, and we're making it smaller, all those terms smaller by multiplying by 1 over j. Do you see it? Taking a fraction of that. So this converges by comparison to this geometric series that converges. Does it make sense? Okay, what about now? This one's different. What about this one? Converge or not? Why is this different? So you see the 1 over 3k to the fourth as the largest term, and you think, oh, that's converges. But what are these? How do these terms compare to 1 over 3k to the fourth? Are they bigger or smaller? Bigger, because it's a smaller denominator. So what I have is my terms of my sequence are bigger than 1 over 3k to the fourth. So I have a series that converges because it's a p series with p equals 4, and I have terms that are all greater than those, right? These are greater than these. Conclusion. This converges. All my terms are greater than the terms of the one that converges. What can you conclude from that? What's that? So you're kind of in a pickle here. You can't really conclude anything, right? It may or may not converge. But what do we suspect? What do we think? Because of the fact that the leading term is 3k to the fourth, we suspect that this is still going to converge, even though all these terms are bigger. And it does, because as k, so this is a different rationale. So this is really kind of like an indirect comparison. It's like we can't use direct comparison here because it doesn't work. So as k gets big, our sequence 1 over 3k to the fourth minus k cubed minus k. What does that approach? It really becomes like 1 over 3k to the fourth, because for big values of k, k cubed and k disappear compared to k to the fourth. Right? So when k gets really, really big, these become kind of inconsequential, and all that really matters is 1 over 3k to the fourth, which converges. It's like what? It's like this is, in the long run, this sequence is becoming like the p sequence 1 over 3k to the fourth. And because in the long run it becomes that sequence, we can still conclude that it converges. But we can't do it by direct comparison like we did the first three, and like we wrote out in the definitions. Okay? So this is kind of like what we call like an indirect comparison. Let k get really, really big, and then this thing will become like 1 over 3k to the fourth, which converges. That's kind of what indirect comparison is.